So when we talked about myoglobin, we indicated that myoglobin had a hyperbolic binding curve, and that's because it exhibited non-cooperative binding. When we talk about the binding that we see for hemoglobin, it exhibits sigmoidal binding, and so that is indicative of cooperation. So when you think about sigmoidal binding, that S for sigmoidal should remind you that that curve is S-shaped. And an S-shaped binding curve indicates cooperative binding. And maybe it'll make sense that myoglobin couldn't have a sigmoidal binding curve because it's only one subunit binding oxygen. It's a monomeric protein. So we can't have cooperation when there's only one thing doing the binding. When we have hemoglobin, there's 4 subunits. Okay? And what's going to happen is when one of those subunits, and if you haven't watched the other video that talked about T state and R state, make sure to do so. When we have one of these hemoglobin protomers binding oxygen, it's going to change from T state, not binding ligand, to R state, able to bind ligand. Now, what's unique about what happens with hemoglobin is the R state, T state of all 4 of these subunits is all or nothing. So the first protomer that binds oxygen and changes from T state to R state forces the other 3 to also change from T state to R state, even though they didn't bind oxygen yet. But because they've now changed their shape and are R state, what they're going to be able to do is bind oxygen more easily. So this cooperative binding really means that the first binding event affects the others, and in this positive cooperativity, the first binding event makes the others easier. So the first binding event makes the others easier, and we call this cooperative binding. Okay, so let's make sure we look at this plot now and recognize sort of what's happening here, right? We're also looking at fractional saturation, just like we did with myoglobin, but this is fractional saturation as a function of PO2, so that property of the environment. And again, we're going to see halfway values here that are important. So we already sort of talked about this halfway value here for myoglobin. But what we can see, this is a really important thing to recognize, is that when we have a binding curve that is more to the left, that represents something that binds more tightly. When you have a binding curve that shifts to the right, you do not bind as tightly. Okay, so just by looking at this curve, we can see that hemoglobin does not bind oxygen as tightly as myoglobin, right? So, and we can do that by holding our fractional saturation constant, looking where we intersect our plots, and we're going to intersect this plot at 2 important values, okay? The P50 here that we have for myoglobin, and that's a number I want you to know, that's 2.8 torr. And then the P50 for hemoglobin, which is 26 torr. Okay? And the fact that the P50 for hemoglobin is greater than the P50 for myoglobin, this tells us that myoglobin binds oxygen more tightly than hemoglobin. So myoglobin binds oxygen more tightly than hemoglobin. And again, that's because the P50 for myoglobin is less than the P50 for hemoglobin. And that's really important because hemoglobin is the one that moves around in the circulatory system, picks up oxygen in the lungs, travels down to the tissues, and it needs to be able to let go of it, and myoglobin needs to be able to pick it up. So sort of that downstepping of P50 values is really important for that. Okay, so a couple of other important things to point out on this plot, and we're going to look at some specific points and ranges in this plot. When we're talking about venous pressure, this is really the pressure that we experience when we're in the tissues, and it's about 30 torr.
I didn't get that. Could you try again?
Okay, when we have arterial pressure, that's the concentration that we have in the lungs, and this is about 100 torr. Okay, so 3 points that I'm going to kind of highlight here. Okay, and then we're going to look at the differences between these points to recognize different things that are happening either within hemoglobin or between hemoglobin and myoglobin. So this is one point that I'm going to look at. This is another point that I'm going to look at. And then here's my third point. Okay, so I'm going to define the difference between these 2 points as region A that we're going to talk about. And then the difference between these 2 points is region B. Okay, so let's talk about what's happening between these different ranges, these different regions, these points. When I'm talking about this A region, I'm looking at the same line, but 2 different environments on that same line. Okay, so what I'm going to have is I'm going to have the same protein. I'm going to be talking about hemoglobin. Okay, so that's going to be the same line. And then what I'm looking at is I'm changing the environment. So I'm changing the environment. And I'm talking about what happens when I go from the tissues to the lungs. Okay, so going from this point to this point talks about what happens in terms of the fractional saturation for hemoglobin as I go from an environment in the tissues to an environment in the lungs. So really what we are representing here is the loading and unloading of hemoglobin with oxygen. So this reflects the loading and the unloading of hemoglobin. Okay, so when we are up here, this represents hemoglobin in a very oxygen-rich environment in the lungs, and it's going to be nearly fully saturated. So we are loaded here. And as hemoglobin travels through the circulatory system to our distal tissues, the oxygen concentration is going to change, and we get to a situation where hemoglobin is much more likely to unload its oxygen. So this trip back and forth represents the change that hemoglobin experiences between the lungs and the tissues environment changing, and that's going to either allow hemoglobin to be loaded with oxygen or then let go of it so that it can go and be delivered elsewhere. And that gets to what we see with this B domain. So this B domain represents the same environment. We're staying in the tissues, but now we have a change in protein. So this is the same environment. We're staying in the tissues, but we're changing our protein. Okay? We're talking about what happens when we change that oxygen going from hemoglobin to myoglobin. So this B domain, this B region, really represents and reflects the transfer of oxygen from hemoglobin to myoglobin. So again, if we draw on here, right now I'm sitting here and I've got oxygen that was bound to hemoglobin, but as I've changed my environment and now I'm in the tissues, really only about half of those populations of hemoglobin wants to hold on to that oxygen. Going back to our bucket brigade analogy, what this really means is about half of our population of firemen decide they want to dump their bucket. And this is a really important thing to indicate that we don't have each set of 4 firemen dumping half of the water or oxygen out of their bucket. What it really represents is half of our population of foursomes of firemen dump the entirety of their bucket. Because remember, hemoglobin either has all 4 binding oxygen or all 4 not binding oxygen. So a 50% fractional saturation doesn't mean we've got 2 of those firemen binding oxygen and 2 not. Each hemoglobin molecule is either fully bound to 4 oxygens or not bound to any. So that 50% really represents a population. So what happens is when half of our population says, hey, I'm going to dump my bucket, myoglobin is more than happy to pick up that oxygen. Again, because it has such a small P50 value, it's happy to scavenge and soak up any of that oxygen that's kind of released and let go of by hemoglobin. Okay, so we effectively transfer oxygen from hemoglobin to myoglobin in the tissues because of that gap. Okay, so the last thing to kind of mention here, and this is going to tie into how we can sort of manipulate this, is the position of this point is key. So the position of this point is key. Okay, and this really represents the idea that we can sort of affect this transfer of oxygen from hemoglobin to myoglobin. So let's imagine this. If we were to move this point down, okay, if this curve were to go through kind of a lower point that was there, that would mean that we would have a more effective, more efficient transfer because our bucket would be dumping more, if you will. On a population level, a greater population of hemoglobin would be fully dumping their buckets. So our ability to shift this point down, effectively changing the P50 value of hemoglobin or letting more hemoglobin let go of their oxygen, is going to have a significant effect on this piece. So we're going to learn later on about how we can affect this point. And this point is also important to think about, because what if we were in a high altitude environment? What if we were existing in a point where we couldn't fully fill up our bucket because our environment was not conducive of that? So once we sort of run through and understand how all of these pieces fit together, we'll then sort of layer on, well, how does your body tweak this? What happens, for example, if you're exercising very vigorously and you're in a state of metabolic acidosis? Or what happens if you're in a high altitude environment? Or what happens if you do certain things that are going to affect where this point is? Okay, so we're going to talk about lots of examples of that as we apply and think about how we affect hemoglobin and myoglobin oxygen binding.